Those who are online, are you able to see my cursor? Those who are online, can you please respond? Yeah. So shall we get started? So I asked you to revise two concepts and come, no? What were they? Drift velocity and why is no one responding? I'm not sure if I'm audible or not.
Sir, the slides are small, sir. We can't see.
Sorry?
We can't see the slides, sir. They're small.
That's what I was asking. But how about my voice?
It's clear, sir.
The slides are smaller.
Yes.
Yes, sir.
Now is it big?
Yes, sir.
Yes, sir.
Okay, but 1 minute, this should not be the case. We time this issue. Follow. You just keep revising. No, sorry. Sorry for this. Is it big now? Guys, can someone respond, please?
Yes, sir.
Sorry, it's big, no?
Yes, sir.
Sorry. I don't know why these issues are coming again and again. Anyways, we'll get started. So, any doubt from previous class? Is everything clear? Right. Can we just recollect the concepts that we saw? What is that we saw yesterday? So first we try to understand the basic terminologies like what is current, what is potential difference, right? So I hope that has got registered. Then the concept on which we concentrated is how the electrons inside a conductor are actually moving. So under what scenario? When the external source is not connected and when the external source is connected. When the external source was not connected, how are they moving? Random motion. And it is happening because of thermal agitation. It is because of the regular temperature that is present around the conductor, right? Whereas when you connect the potential source, what happens? Because of the can you tell me the sequence of events that is happening? So when you connect the potential source, what happens? First thing is electric field is generated. Due to the electric field, the electrons experience force. Sorry. Due to the force, they start experiencing acceleration, and due to that acceleration, they attain final velocity. And that average of all those final velocities is what is called as drift velocity. So drift velocity is the effect, electric field is the cause. So effect divided by cause, that is drift velocity divided by electric field, has a name. It's called mobility. So mobility signifies how fast or slow the electrons are able to move inside a conductor. But an important point is under the influence of electric field. So wherever that electric field has to get generated, what is needed? Potential difference. That is why I say that both the points are related. Having said this, now we will see another topic. So this is how a conductor is. So when you take a conductor, you have electrons present inside. So what are these electrons? They are the free electrons. Right. You have a positive terminal here, negative terminal here, and there is an electric field which is directed like this. And due to the positive and the negative terminal, there is a potential difference that is going to exist. So if I take the length of the conductor to be L and the area of cross section to be A, right? These are the two things I'm taking. So what is going to be the volume of this conductor? So volume is going to be equal to A multiplied with L. Simple. So it's going to be A multiplied with L. Now the question is, suppose there are n electrons present inside the conductor. Suppose there are n electrons present inside the conductor. Suppose there are n electrons that are present inside the conductor. What is going to be the total charge present in it? Obviously, capital N multiplied with the charge of each electron. That is going to be N into E. Let me call this as 1. Right. Now, what is going to be the current that is constituted? What is the current that is flowing within the conductor? So what is going to be the current that is flowing within the conductor? It is going to be N into E divided by the time it takes. Why is it so? Because it is charge per unit time. So charge is N into E divided by time. Now the question is, how much time is it taking for an electron to go from the negative to the positive terminal? How much is the distance it is able to travel? Or how much is the distance it is supposed to travel to complete the circuit? So it is able, it needs to travel a distance of L, right? So if I say distance traveled by electron is going to be L. From here I can I say the time is equal to distance by speed. So what is the distance it is traveling? L. But we know the fact that on an average, each electron has velocity of Vd, which is a drift velocity. So that is the average of each electron speed, right? So it is going to be Vd. Makes sense? Right. So let me call this as second equation and let me call this as third. So what I basically did is I tried to calculate the value of current in terms of the charge per unit time, but we know that the total charge inside the conductor is capital N into E, and I calculated the time using the basic formula of distance by speed and wrote this. So what I'm going to do is take the third equation and plug it into the second one. If I do that, I'll be able to say that the current is equal to N into E. I'm not disturbing the whole divided by what is going to be the time, L divided by V into D. So this N into E into Vd, the whole divided by L. Makes sense? The Vd goes to the numerator by this thing. So what is this? Sorry, wait. Correction. So this N into E into Vd divided by L is there. Now what I'm going to do is, since area of cross section is getting related to a parameter of volume, observe. If I combine area of cross section with length, if I multiply both, I get a parameter volume. And when I talk about a conductor is basically cylindrical in shape. When it is cylindrical, it's a three-dimensional shape. Generally for three-dimensional surfaces, when you speak in terms of density, you try to speak in terms of volume density. So how can I bring volume density here? By multiplying with A and compensating with A in the denominator. So I'll multiply it with A and dividing it with A. I hope you understood the logic of why we are doing this. That is more important, right? Why is it so? Because the conductor is three-dimensional. For a three-dimensional shape, we define volume density. So A into L is going to give me volume. Am I right? So look at the way I'm going to write. Capital N divided by A into L, one parameter. E into this A, I'll combine it here, A into Vd. The same expression is rearranged in this form. So A into L is volume. Capital N is the number of electrons. Listen to this very carefully because I'll be using two terms. One is number of electrons and I'll be using something called as number density. So for number of electrons throughout physics, for number, you always use capital N. For number density, you always use small n. So here, if you observe the number of electrons per unit volume is going to give me number density. So I will replace that with small n, right? Into E into A into Vd. So this is going to be the final expression for the current that is flowing through the conductor in terms of measurable parameters. So what I would say is this is the relation between the current in terms of drift velocity. That is why we saw drift velocity first. The next concept that we are supposed to know is this. So the heading is going to be the relation between electric current and drift velocity. Okay. So is every point clear? So make a note of. Those are online. Is everything clear?
Yes, sir.
Write it down.
Sir.
Then I took time as L by VD. So those are online. I hope it is clear. Everybody finished it, right? So from here, we will see another important relation. So we know that I is equal to NEA into VD, right? If I rearrange this equation, I will be able to write it as I divided by A is equal to NE into VD. if you observe, this is basically the amount of current which is flowing per unit cross-sectional area. If you take this to be the conductor, there is current flowing through this. The amount of current flowing per unit cross-sectional area is what we call it as current density. So this is also density only, but the name given to this is the one which is in the numerator. What is it? Current per unit area. So it's called as current density, which is represented by the symbol J. Okay. What do you call this as? You call this as current density. And remember, current density is a vector quantity. So current density is a vector quantity. And what is going to be the unit of it? Obviously, unit is going to be, look at it and tell me. Don't look at the right side. Look at the left hand one. Ampere per meter square. So it is going to be ampere per meter square. So this is another important term that we are supposed to. So please make a note of it. Here, we'll go to the next important topic.
Sir,
Hmm.
sir, what is small n here?
Small n is number density. So it's called number density. It is the number of electrons per unit volume. Number of electrons per unit volume is called as number density. Okay, if at all you will forget, please make a note of it. Clear? Shall I proceed? Okay. So the next topic we are going to see is, suppose, let's say, this is a conductor again. Electrons are there, positive terminal, negative terminal, and there is an electric field in this direction. If this is going to be the length, if L is going to be the length of the conductor and A is going to be the area of cross section. So we know that I is equal to NEA into BD. Right. So let this be equation number 1. But what do we know about drift velocity? So we know that drift velocity is equal to small e into capital E divided by m into tau. Right. So let this be the second equation. So I'll take this expression and plug it here. If you observe, I didn't put a minus sign here because I'm only concerned about magnitude. Minus sign is used only when you need to speak about direction. So here everything is drawn, so I didn't use it. I is equal to NEA into, observe. In the place of BD, can I write it as E into capital E divided by M into tau? Right. So let this be the third expression. It is a combination of first and second. But what is a relation we already know that is existing between electric field and potential difference? So we know that electric field is equal to the negative of potential gradient, but since they have already drawn the direction here, and you know the potential difference that is existing between positive and negative terminal, if I say that the potential difference existing is V, can I write E is equal to V divided by L? Right. So if I take this to be 4, can I take this and plug it here? So the logic is simple. First, I wrote the expression for current. Second, I wrote the expression for drift velocity. I combined both. Then you got a third expression for current in terms of electric field. I'm using a known relation between electric field and potential difference. Now I'll take this 4 and put it into 3. So you will get another equation like this. I will be equal to NEA. I'll take this E here divided by M into, I'll have this tau also here. In the place of E, I will replace it with V divided by L. Right. Now I'm going to rearrange this equation, which implies I'll keep this V here. So I'm just writing this V on the left hand side. Okay. So V is going to stay at this place. Now what will happen is all other parameters will get shifted to the right. So V will be equal to M into L, because M and L are in the denominator, go to the other side. M into L divided by N into observe. E into E is going to be E square. A is A only, and the tau will go to the denominator. The whole thing multiplied with current. So this whole thing is going to get multiplied with current. So if you observe this expression, this whole thing can be replaced with a symbol R, which you already know in the name of resistance. So this is the expression for V is equal to IR, which is nothing but your Ohm's law. So in your 10th grade, you learned this as Ohm's law, right? Now we will see why Ohm's law is defined in that way. So how does the statement start? It says when the temperature of the conductor is a constant, right? When the temperature of the conductor is a constant, the current flowing through the conductor is directly proportional to potential difference. Okay. In some books, they will say that the potential difference is directly proportional to current. That is wrong. Because anything that is proportional should always be a dependent quantity. Here, current is the one which is dependent on the potential difference. Try to understand what I'm saying. Current is getting generated because of the potential difference you connect. But the potential difference value is not getting generated because of current. Means you go to a shop and buy, the potential difference is fixed. You buy a battery, its potential difference is fixed. If you connect a 1.5 volt battery, there is a specific amount of current that can flow. So current is controlled by potential difference, but the reverse is not happening. That is why I'm stressing on this point. Make it a practice that whenever you are defining proportionality things, make sure that the right hand side is a dependent quantity and left hand side will be a independent quantity. Okay, I'm sorry, I made a mistake. It should be reverse. Left hand side should be a dependent quantity and right hand side should be a independent quantity. Okay, so here what is happening is current is directly proportional to the potential difference, provided what? The temperature is constant. Why they are saying it is because we write V is equal to IR and you introduce this R as a constant of proportionality. Now we will understand when you look at the actual meaning of R. When temperature changes, since conductors are metals, when you supply heat to it, they expand. So L will change. Similarly, what can change? A will change. And most importantly, the relaxation time will change. Because when you supply temperature, the kinetic energy of the particles will increase. I repeat, kinetic energy increases. The time existing between two successive collisions will decrease because they start moving faster. You're able to understand? So this expression is what is Ohm's. So we have seen the derivation of Ohm's law. Am I clear with this? It's simple, right? So if you look at the operation, it is very simple. Make a note of it. 1 by R. Constant should have been 1 by R, which is conductivity, conductance. V by L. Yeah. Yeah. Shall I proceed? Okay, listen. So we saw Ohm's law where R is coming out to be M into L divided by N E square A into tau. M into L divided by N E square A into tau. Now I'm going to make a small rearrangement. From here, can I write R is equal to M divided by N E square tau into L divided by A? So if you observe, this is similar to the expression R is equal to rho into L divided by A, which says that this parameter is called as resistivity. So this is the resistivity of the conductor. If you observe, when I talk about resistance, M into L divided by N E square A into tau, the resistance is dependent on temperature. It is dependent on the length and area of cross section of the conductor. Whereas if you look at resistivity, right, resistivity is equal to M divided by N E square tau. So resistivity depends only on this this temperature changing parameter, which is the time constant, which is a relaxation time. Okay. Now, resistivity, unlike resistance, is not dependent on length or area of the conductor. It depends only on the material. For a given material, resistivity is constant, irrespective of its length and area, but it depends on temperature. Why does it depend on temperature? When temperature changes, what can change? The relaxation time will change. So just to make a note of it, if I have to frame a relation, so increase in temperature, so capital T is used for temperature. So increase in temperature leads to decrease in relaxation time. Reason? Kinetic energy of the particles go high. So when the kinetic energy of the particles go high, the relaxation time obviously decreases. Okay. So these are all the important points we need to understand with respect to Ohm's law, resistance and resistivity. Yeah, make a note of it. Yeah. So those who are online, are you done?
Yes, sir.
So just now we understood two important things. What is it? Resistance and resistivity both are dependent on temperature, right? So what we are going to see now is temperature dependence of resistance and resistivity. So we are going to see the temperature dependence of resistance and resistivity of whom? Of a conductor. Okay. So if you observe R after a change in temperature, if I call it as R final, okay. Let's say there is a conductor whose initial resistance is Ri. resistance initially is Ri after some temperature is supplied. So here I'm taking the example of after some heat is being supplied. Okay. Correction here. Cannot say temperature is supplied, heat is supplied. After an increase in temperature, let's say its resistance becomes R final. This is for sure. So R final is written as R initial multiplied with 1 plus alpha into delta T. So this expression is very much similar to what you would have seen in thermal expansion of solids. You would have written L is equal to L naught into 1 plus alpha delta T. A is equal to A naught into 1 plus beta delta T. You would have seen, no? It is something similar. Where this RF is called as the final resistance. RA is called as the initial resistance. Alpha is called as the temperature coefficient of resistance. Okay. And delta T is obviously called as the change in temperature. So here an important point to be noted is the temperature coefficient of resistance for a conductor is always positive. I have to stress on this point. Temperature coefficient of resistance for a conductor is positive. The meaning of it is if there is an increase in temperature, resistance will also increase. If there is a decrease in temperature, resistance will decrease. You can ask me why are we even telling that? Because for materials which are called as semiconductors, which we'll be seeing at the end, they have negative temperature coefficient, meaning if the temperature increases, their resistance will go down. They're inversely proportional. So here, what do I mean by positive is they are directly proportional. Increase in temperature, increase in resistance, decrease, decrease. That's the story. Okay. So this is how the temperature coefficient, temperature dependence of resistance will take place. Similar is the case with resistivity. All that you need to do is change the symbols here. Rho F is equal to rho initial into 1 plus alpha into delta T. Here you can take this alpha to be the temperature coefficient of resistivity. Okay. So when we are solving problem, these values will be mostly given. So what will happen is any one of the parameters will be an unknown from this, and that is what we will be expected to find. Okay. So first make a note of this. Shall I proceed? Those who are online, shall I?
Yes.
So I hope it is simple till here, no? Anything that is tough? Okay. So listen to this. We are almost done with half of the chapter. So the next part that we are supposed to see is, first I'll do one thing, I'll complete the theory, then I'll concentrate on problems. Okay. The next part that we are supposed to focus is resistors in series and parallel, which you already know, right? Then we need to understand some laws. We saw what is Ohm's law, right? V is equal to IR. You have already applied it enough in your 10th grade. We'll be seeing two other laws which are named as Kirchhoff's first law and the second law. Okay. After that, we'll be seeing another concept called as Wheatstone bridge. With that, the chapter is done. So maximum 3 classes. So we'll be done. Okay. Shall I proceed? So the next concept you are going to see is resistors in series. Oh, sorry, I forgot one thing. We need to see about cells also. I'll tell you. So write down the next heading as resistors in series. Okay. So the first thing is when you connect the resistors in series, right? When resistors are connected in series, right? What happens is current through each resistor is same. So current through each resistor is the same. Whereas the potential difference gets divided in such a way that the sum of all potentials across each resistor will be equal to potential difference across the battery is equal to the potential difference across the battery. There's a known story, right? So what do I mean by this is, if I take 1, 2, and 3 resistors to be in series like this, and it is connected across a battery of, let's say, a potential difference V. Okay. Then here the resistance is R1, R2, and R3. So this battery is going to supply the current from higher to lower potential, right? So current is going to be I. Now the same current I is going to flow through R1, R2, and R3. But what is going to be different? It is the potential difference. So if I take the potential difference here to be V1, right? Here if I take it to be V2, and here if I take it to be V3, then according to the second statement that was made, V will be equal to V1 plus V2 plus V3. Am I right? No. So if I observe what is V1 here according to Ohm's law. So remember, whenever you need to apply Ohm's law, have this point in your mind. Whenever you are asked to apply Ohm's law, the whole circuit where you're applying Ohm's law should have only one battery and one resistor. There are multiple batteries or multiple resistors, you need to convert them as one and then do it. So here what I'm doing is, though we have only one battery, but I've considered V1 to be the potential drop existing only across R1. So that is why I'm applying Ohm's law only across the first resistor. So one potential difference is equal to the current that is flowing through this multiplied with one resistance. That is why I wrote V1 is equal to I into R1. But can I write V is equal to I into R1, V is equal to I into R2, and V is equal to I into R3? No. Right? So V is equal to I into R1. Similarly, V2 will be equal to I into R2 and V3 will be equal to I into R3. I'll take all these values and put it in the right hand side. So if I take these values and put it here, can I say I is common in all? I into R1 plus R2 plus R3. But my question is, what is there on the left hand side? So what I need to do is, listen to this carefully. We call something as an equivalent circuit. What do you mean by equivalent circuit? Replacing all the passive devices, that is the resistors here, replacing all the resistors with one resistor which does the same work done by all these three resistors put together. See, this will do some work, this will do some work, this will do some work. No, I can replace everything with one which can handle all the three. Right? So that resistor's name, I will give it as RS. But where is this RS connected? It is still connected across the same potential difference. V, and here it is going to be I. So what can I write V as? I into RS. So I will take this as the first expression, this as the second expression. So here I know it is V only. V is equal to I into R1 plus R2 plus R3, first one. V is equal to I into RS, second one. Using 2 and 1, what are you going to get? So left hand side will be I into RS is equal to I into R1 plus R2 plus R3. I and I are gone. RS will be equal to R1 plus R2 plus R3. Right. So this is going to be the equivalent resistance for the diagram that we took. If there are n resistors, if n resistors are connected in series, what will happen? RS will be equal to R1 plus R2 plus so on till Rn. Right. So make a note of this. Okay. Yeah. Okay. So obviously parallel, you know, it is going to be the reverse scenario, right? And one more update is you have to stop the class by now because I need to shift the laptop inside. That is one thing. Secondly, as I mentioned, no, we'll try to concentrate more on problems. Remember, I discussed 2 days back that we need to start working on the pre-recorded content as well. That is, during the next 3 days, I want you to go through the content and come because now we have holidays also, right? So I'll record the content and give it to you in the app itself. Just go through them and come, so that from Monday we'll concentrate on doubts and problems. It's possible only when you work at home. Okay. So that's the update. Yeah. Any other doubt? Everything's clear, no? Okay then. So we'll stop with this. So those who are online, any doubt?
No, sir.
Okay, we'll wind up, guys.